I have good or bad news, depending on your perspective. This is the section of the class where we start reactions, and that means we have to deal with reaction intermediates. The reaction intermediate that you actually deal with throughout most of the semester is the carbocation. So we've got to spend quite a bit of time learning about carbocations and getting comfortable with them. If you don't develop a sense of comfort with carbocations, the semester is going to be very, very difficult for you. So let's spend some time getting used to them and getting to know how they work. A carbocation obviously is a positively charged carbon. Carbo stands for carbon, and cation means a positively charged ion. These are two examples of carbocations. You can see that they've got carbons with positive charges. And each of those carbons only has 3 bonds. And that means that, not only are these carbons unstable because they're positively charged, but they're unstable because they lack their full octet. That means they're desperate for electrons. That makes them really electrophilic. Carbocations are strong electrophiles. What electrophiles are is positive or partial positive molecules that are attractive to nucleophiles. They want to be attacked by things that can donate electrons to them. So again, carbocations are great electrophiles and they're ready to be attacked. An important thing about carbocations, and something that we're really going to focus on here, is that a carbocation's stability determines the rate of a reaction. So we don't just care that carbocations exist, we care how stable they are relative to one another. So let's take a look at some different types of carbocations and rank their stabilities. Let's take a look first at these standard carbocations that are discussed in your book. This is a tertiary carbocation. We can see that the carbon that's carrying the positive charge is attached to 1, 2, 3 other carbons. And what makes that carbocation a little bit more stable than others is you can imagine this carbon is electron deficient and it would like to have more electrons. So you can imagine it calling out to its friends and neighbors saying, "Can anyone donate some electrons?" And it's got 3 neighbor carbons that can send electrons down the shared bonds to help ease some of its positive charge. Now, a primary carbon only has 1 neighbor to help it out, and a methyl carbon has no neighbors to help it out because hydrogens can't donate electron density down their bonds. So just looking between the methyl and the tertiary, we can see that the tertiary would be most stable, while the methyl would be least stable. This process of donating electron density down the bonds is called induction. Now let's look a little bit further at allylic and benzylic. These aren't actually listed in your chapter in the rankings of carbocations, but they're going to become so important later on. And actually, in your next chapter, they're going to be so important. You might as well talk about them now. An allylic carbocation is when the charge appears right next to a carbon-carbon double bond. And resonance allows this charge to move right here. And what that means then is that this carbocation actually has a second resonance structure. And the more resonance structures a compound has, the more stable it is. So that means that this allylic structure is much more stable than the tertiary structure, even though to look at this carbon, it only appears to be secondary. So allylic carbocations are more stable than tertiaries. And in fact, I could draw a primary allylic structure, and this primary allylic structure would be more stable than the tertiary structure. Even better than allylic structures are benzylic structures, in which the carbocation is right next to the benzene ring. And the reason is that this carbocation can actually move through resonance all the way around the benzene ring, and there are 4 resonance structures for this benzylic carbocation. And again, I could rewrite this as a primary benzylic, a secondary benzylic, and true, there are tertiary benzylics. And any one of those is more stable than any of these. Now, you're not really required to know anything about vinylic carbocations. I put this here so that you would compare and contrast it to the allylic cation. Vinylic cations are extremely unstable, but they look really similar to allylic cations, and I don't want you to confuse them because your test and your quiz likes to try to trick you. A vinylic cation has the charge directly on the carbon-carbon double bond, where allylic has the charge next to the carbon-carbon double bond. This is stable, this is extremely unstable. Don't be tricked by it. Prior to this chapter, when you talked about stereochemistry, it was related to cis and trans orientation on a ring or a double bond, or E and Z orientation on a double bond. But starting in this chapter, you're going to be learning about chiral carbons. Chiral carbons are also called stereogenic centers or just stereocenters. Your professor likes to call them stereogenic centers, but I normally use chiral carbons. Just make sure that you're familiar with both and you know that they're interchangeable. Chiral carbons have to be sp3 hybridized, which means that they're always going to have 4 bonds because it's important that they are bonded to 4 different groups. That's the definition of a chiral carbon. Any carbon that's bonded to 4 unique substituents. Now notice here, this carbon is chiral, but it's bonded to a carbon, a carbon, a carbon, and a carbon. So it can be bonded to 4 same atoms. What's important is the 4 groups that it's bonded to. This is bonded to an ethyl, an isopropyl, a propyl, and a butyl. So as long as the 4 groups that it's bound to are unique, then it's fine and it's chiral. So one of the jobs that you're going to have is to look at a big molecule and identify all the chiral carbons in it. So let's take a look at how to do that. Here's an example of the kind of problem that you might see. You could be given a big molecule like this and asked, how many chiral carbons does it have? And in order to do that, you'll want to be able to ignore the carbons that don't matter and focus on the carbons that do matter. You can ignore any carbons that are touching double bonds or triple bonds because those carbons are sp2 or sp hybridized, and as you know, chiral carbons have to be sp3 hybridized. You can also ignore what I call the ends and the bends. Ends are the primary carbons that are at the ends of a chain, like this one, here and here, here and here. We can ignore those because they are CH3s, and if they've got 3 H's on them, that's 3 duplicate H's, so they couldn't possibly have 4 unique substituents on them. We could ignore the CH2s, or the bends, for the same reason. They have 2 H's, and if there's 2 H's, there couldn't be 4 unique groups. The reason I call them bends is because they look sort of like the bend in a bent pipe, like right here, and here, here, and here, here, and here, and here, and here. There's always a lot of them. But anywhere you see a bend like that, you can ignore it because you know it's a CH2. So really, we're only going to focus on any place that you see a junction of 3 lines or a junction of 4 lines. Those are the only potential chiral carbons. So if we just let our eyes focus on those, you'll see that there's one here, and here, 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 and that's all. So then at each one of these spots, we have to inspect for duplicates. We have to check at each one of these places and say, do we see any duplicate groups? If we see duplicate groups, it's not chiral. But if we don't see any duplicates, then it is a chiral carbon. For example, here we see an ethyl. We see this 2-carbon chain with an OH on it. That's different from this one. And then we see this big chain. Those are 3 different groups. So this is a chiral carbon. And sure, yes, there is a hydrogen that we don't see, but we don't really have to pay attention to it. We just need to check for duplicates and we'll be fine. Here we have this group, an ethyl, and this group. They're all different. So this is chiral. At this carbon, we have this group, and this group. And anytime you have a ring, you need to check and see if the 2 sides of the ring are indeed different. And the easiest way to do that is to sort of take your two fingers and lead them around the two sides of the ring. For example, here's my starting point. That's a CH2 and that's a CH2. Those are the same. So I go to the next spot. Well, this is different than this. These two carbons have different substituents on them. So I've hit a point of the ring where I have a difference. And if you hit a point of the ring where you have a difference before your fingers meet on the other side, then the two sides of the ring actually are different. So this carbon has different substituents. So this is a chiral carbon. When I'm looking here, I'm going to run into the same issue. I have a substituent here, and I have to find out if these two sides of the ring are different. And again, I can check. Those are the same, but then when I get here, these two carbons have two different substituents on them. Therefore, there's no duplicates here. And here I run into the same thing again. This substituent is different, and these two sides of the ring are, again, different from one another. Here's a junction of 4. I have a chlorine, a methyl, an ethyl, and this big mess. That's chiral. And this is a deceptive little spot. I have this big group, a methyl, and a methyl. And it's a very common thing for your quizzes or your tests to have questions like this, where you'll see a wedge or a dash that indicates to you that a carbon is chiral. But just because it has a wedge or a dash on it doesn't mean it's chiral. You always have to check for duplicates. And in this case, that's a methyl and that's a methyl. Those are duplicate groups. So this is not a chiral carbon. So this molecule has a total of 1, 2, 3, 4, 5, 6 chiral carbons. We also can tell based on this how many stereoisomers the molecule has. There's a formula. The number of stereoisomers is 2 to the nth power, where n equals the number of chiral carbons plus the number of carbon-carbon double bonds that are capable of cis or trans or E or Z. So this is a special number of carbon-carbon double bonds. If a carbon-carbon double bond is not capable of cis, trans, E or Z, you do not count it in this number. So let's check. We do have a carbon-carbon double bond, and look, it's on the inside of the chain, and each side of the double bond has 2 unique substituents. So this is capable of cis and trans. So this counts in our N. So we have 6 chiral carbons, wait, is that right? Yep, 6 chiral carbons plus 1 double bond that's capable of cis, trans, E or Z. So our N actually equals 7. So our number of stereoisomers would be 2 to the 7th power. I'll let you put that into your calculator, but that's how you do problems of this type. Typically, they're not going to be this difficult. Let me show you one that's a little bit more like what you might see on a quiz. Let's take a quick look at some nomenclature of carboxylic acids. Carboxylic acids are actually the dominant functional group out of all your functional groups. So whenever you see a carboxylic acid group, you know that that's going to be your highest ranked group. And so your first job is to find the longest carbon chain that contains the carboxylic acid group. So if you're going to name this compound, we want to find the longest carbon chain that contains the carboxylic acid group, and then of course we know that the carboxylic acid group is going to be on carbon 1. So we'll number this way. This would be a hexane chain, but when you have a carboxylic acid, you give it the oic acid ending. So we'd call this hexanoic acid. We'll apply those same rules to this compound. We want to find the longest chain that contains the carboxylic acid group. That chain actually goes in this direction. So this is a pentane chain, and we'll call it pentanoic acid. And you can see that we have an ethyl substituent on carbon 2 and a methyl on carbon 3. So we'll call this 2-ethyl 3-methyl pentanoic acid. And do notice that in both of these situations, I didn't say that the carboxylic acid group was on carbon 1. I didn't call it 1 hexanoic acid or 1 pentanoic acid. your carboxylic acid group is always going to be on carbon 1. It's understood, so we don't have to indicate it in the name. Here's an example of an alpha hydroxy acid. Remember that when you have a carbonyl, the carbon next to the carbonyl is known as the alpha carbon. And so sometimes you're going to see hydroxy groups on the alpha carbon, and those are called alpha hydroxy acids. If we were going to name this one, we know again that our carboxylic acid is on carbon 1. So this is a butanoic acid, and there's a hydroxy group on carbon 2. So we'll just call this 2-hydroxy butanoic acid. And don't forget that you'll also see a carboxylic acid group on benzene. This is benzoic acid. And in this case, since we have a chlorine on the meta position, this is metachlorobenzoic acid.